Hello everyone. So in the last class we have discussed about armature reaction and few of the doubts have been asked, and I request you that you should ask your doubt in the comment box rather than mailing me, okay? Because it will be discussed with everyone so that people will know that you have some doubts. So it is very much feasible for everyone. Okay, so your doubts will be cleared now. So for our armature reaction, we have seen the diagram, that is your which comes first, phi m, how E was affected, and then there was armature reaction was there. Armature reaction was there. So totally, I have told you that cross magnetizing effect, cross magnetizing contributes to torque production, and your demagnetizing or magnetizing effect contributes to EMF production. Now there was a one confusion here, that how sir, how you are saying that, because you are saying that the interaction of flux creates torque. Yes, interaction of flux, because torque is directly proportional to phi r and phi m, right? Main flux and armature flux interaction here. But EMF, let's see, cross magnetizing effect is generally given to because of the R load, resistive load, and this R load is only the real power that is invested. While in demagnetizing and magnetizing effect, we are considering reactive power. Reactive power. So because of this reactive power, we are not able to get this reactive power. Okay, torque means real power. Magnetizing effect gives us a reactive power. So EMF, I think EMF is that you can note down the formula, that is 4.44 F phi m, right? This flux, now this flux modifies to phi m plus minus phi a. Okay, when the EMF is feeding some load. Now there may be this armature reaction may add it, or the armature reaction may subtract it, and because of that EMF voltage will increase or decrease depending upon the effect. So that's why EMF, that voltage is affected by because of the demagnetizing effect. And this demagnetizing is actually, magnetizing or demagnetizing is actually a reactive component, and cross magnetizing is the real component. So this is the whole picture. Okay, so let us now, I hope it is clear now. Now basically, in your machine there are three types of this. I am now going to draw the simplest circuit for a alternator. Rather than drawing the biggest part or stator and rotor, I am going to draw the simplest circuit. This is your resistance, then this is an inductance, and then this is again an inductance. Now what are these things? So this is my E, this is the EMF induced, and EMF induced because of the field. We give the field and flux, and that creates EMF, right? So this is my EMF. Flux can be very DC excitation on the rotor side, and that creates EMF. Okay, then there is a drop in the stator, that is called armature drop, armature resistance. Okay, armature resistance. Then there is XL, this is your leakage reactance. Okay, and then there is XA, that is armature reaction. So this whole will give you XS, that is synchronous impedance. Okay, so RA is armature resistance, armature resistance. XL is leakage reactance, leakage reactance, XA is armature reaction, reactance, armature reactance, and XL plus XA is XS, that is called as synchronous reactance. Okay, so your alternator will have an EMF, it will have resistance, and it will have a leakage reactance and this. So, and this is your terminal voltage, that is V. This is the voltage that goes to the load. Now, why I am drawing this? So I have already given you that this is my rotor, and this is the diagram which we were drawing previously, right? This is the three phase. Now this whole circuit is converted to this right now. Okay, this is my electrical circuit that is coming, and this is my terminal voltage that is going to the load. This is the EMF that is going to the induced. Okay, now considering the above diagram, what we can say, that if there is a current, that is, suppose this is an current IA is going to flow here, and suppose there is a load connected here with a, suppose this is a load that is connected, RL load is there, RL load is connected to the circuit, and EMF is induced. Now what will be my phasor diagram? Let us draw the phasor diagram. So this is my phi m. Okay, then this axis is my phi a. Okay, I'm drawing dotted line because I will later on I will add it up. Now what is my EMF equation? EMF equation is equal to, if you write the KVL equation here, I can write E is equal to V. This is all vector. E is equal to V plus IA RA plus J IAXA plus J IAXL, right? So these are your perpendicular components. I hope you remember these things. Now from the EMF equation, I will draw the phasor diagram. Let us see the phasor diagram. This is my phi m, and this is the E axis. Okay, E axis will be there. Now what happens that E has a load that is inductive load, so no doubt there will be V is lagging, this is my V, and there is one more lagging load, that is IA. Okay, RL load is there, so there will be some phase angle, that is phi. Okay, and this is your delta. So delta is actually the angle between E and V. Okay, so if I am writing E as vector, you can write E at an angle 0 and V at an angle delta. So this angle, this axis is 0, this axis is considered as 0, and this axis will be minus delta, lagging minus delta. So I can write it like this, V at an angle minus delta. Okay, now we will draw the phasor diagram. So IA is in this axis, so IARA, I hope you have drawn the phasor diagram in transformer. I am not going to discuss the phasor diagram how it is drawn. IARA, so IARA, the drop will be in phase or in parallel with IA. So this is your IARA. Okay, and IAXL XA, IAXA is will be perpendicular to this. So I'm drawing some other. So this is IA XA, right? This is perpendicular to IA, and these are parallel lines. Okay, these are parallel lines. And IAXL will be perpendicular, again perpendicular. Okay, so I am drawing IAXL, and this magnitude there is one more issue is there, that IAXL, this is IAXL. Okay, IAXL will be always small. XL value, leakage reactance, will be small, and leakage armature reaction will be more. So this is IAXA, IAXA, and in the same axis there will be IAXL. This should be a straight line. I am not able to draw the straight line. Okay, this is IAXL, this is IAXL. These are all in the straight line. Because there is a small gap here, so that's why I am not able, and this should be perpendicular. Okay, so this all will be in a straight line, and this will go to match this EMF E. This is a straight line. Okay, so what is my this is the phasor diagram, and always remember XL will be more than XA, sorry, opposite XA XL. Okay, XL will be less than XA. Okay, armature reaction will be always more. Okay, so this is the whole equation or phasor diagram of this equation, that is you are getting. Okay, now what I am doing, I want one more thing, that what is I want how we can take E. This is the phasor representation. Now this is a triangle, this triangle ABC. ABC is a right angle triangle. Right angle triangle ABC. Okay. ABC is a right angle triangle. Okay. So what I am going to do, I will take some component. So this is my V. So this is my cos component. This distance is V cos phi. Okay. V cos phi. And this distance is V sin phi. So two components, this distance is this. Okay, this same distance, this distance is nothing but this distance. So this is V cos component, this is V, and this is IARA. Okay, so IARA is this distance. So what I can say, IA, so this is my IARA. Okay, so what I can say, that triangle ABC, so BC length, if you see BC length of BC is V cos phi plus IARA. Okay, length of AB if you see, this length of AB is V, V sine phi plus IA XL plus IA XA. Okay, so this is the two lengths of, so using Pythagoras theorem, what you can write? Using Pythagoras theorem, you can write that E square is equal to A V cos phi plus IARA whole square plus V sin phi plus IA XL plus XA. I'm taking IA as common, whole square. So what is this? This is AC square, hypotenuse square, is equal to BC square plus AB square, right? This is the same formula, Pythagoras theorem, right? Now, this is because of which load? RL load. Okay. For RL load, inductive load, whenever there is an inductive load, this sign will be positive. Okay. For RC load, that is your for capacitive load, this sign will be negative. Okay. I hope you know this. The current will lead. Okay. So current will lead in RC load. So it will come this side. So you can draw that for RC load. So this is the whole picture for E. Okay. So what I can write now? What I can write now is that E is nothing but root under this whole equation, right? V cos phi plus IARA whole square plus minus V sin phi plus minus, oh sorry, one problem is there, this minus, not this, the here for inductive load, for capacitive load, here should be the minus. Okay, for capacitive load this minus, plus minus IA XL plus XA whole square. Okay, so this is the whole E, EMF induced. What is E? E is the EMF. Now, seeing the figure here, see the figure here. Now, seeing from the figure here, we can say that delta is the angle between E and V. Delta is the, this is called load angle. I have already discussed this in our torque production, load angle, and it is nothing but E and V. Phi is the angle between V and IA, armature current. Okay, so this is the difference. Now this whole angle, phi is the power factor angle. This whole angle is called psi. Psi is the angle between E and IA, and this is called as internal power factor. Internal power factor. Okay. Now, why I am discussing this whole thing? This whole thing is discussed because whenever you are manufacturing a alternator, you have to give one specification by testing. Whenever you are manufacturing an alternator, you have to give an specification that is called as voltage regulation. What is voltage regulation? It is nothing but difference between E and V upon magnitude difference between E and V upon V. And this is one of the parameter multiplied by 100%. So voltage regulation means difference between E and V. Okay. Now, how you when an alternator is operating, it will produce V. Suddenly you take out the load. If you take out the load, no current will flow. Open circuit the load. Suddenly you take out the load and you measure the voltage here. You measure the voltage here by voltmeter. What you will get? If no current is there, there will be no drop. IA is equal to 0. Okay. What we are doing? If we want to measure the E of it, so what we will do? What we will operate the machine, operate it, and then suddenly open circuit it. Open circuit means no current is going to flow here. Okay. When no current is flowing, then the drop across RA and XL and XA will be 0. Okay. That means the voltmeter will directly measure E, right? E, and that voltage and your normal operating voltage minus it or subtract it, that will give you this. From this formula, you are getting E. So our main purpose to find E is to define the voltage regulation. Okay. Our main purpose to find E is to find the voltage regulation. So for voltage regulation, if you can find out E, then only you will be able to find everything. Okay. So this lecture I am ending it here. Our next lecture will be will talk more on voltage regulation.